All right, welcome everyone to the session on symbolic methods for verification and matching. We've got four great talks prepared for you. So the first talk will be solvable tuple patterns and their application to program verification by Naoki Kobayashi, Ryosuke Sato, Ayumi Shinohara, and Ryu Yoshinaka. And Naoki will be giving the talk.
Okay, so I'm Naoki Kobayashi from the University of Tokyo. So today I'm going to propose the notion of solvable tuple patterns for quick inference of relations among sequences from only a few positive samples. So here is a sample data, and we want to find a common relation among x, y, and z. We use a kind of patterns to represent the relation. So in this case, this means that the third element is a concatenation of the reverse of x and y. Okay. And we have come up with a very simple, efficient algorithm for inferring this kind of relation and applied it to automated verification of list manipulating programs in the framework of constraint Hom clauses. And it turned out to be quite effective. So there is an annual competition on CHC solvers, which serve as a common backend for automated verification tools. And we have won the ADT category of the competition for 2 years in a row. And as this graph shows, our tools significantly outperformed existing tools. So here's some motivating example. So this is an OCaml program which first defines a recursive function rev_a, which takes two lists as arguments and returns a list. And the main function asserts a property of the rev_a function. Okay. And suppose that we want to show that this assertion never fails. Okay. And in this case, naive induction would not work because assertion contains 3 recursive calls of rev_a, and each recursive call takes different lists as arguments. Okay? So the only reasonable way to prove the absence of assertion failures is to infer the invariant on rev_a that it actually computes the reverse append. Okay? But the question is how we can find it automatically by just looking at programs. And we take a data-driven approach for that purpose. And to that end, we introduce the notion of solvable tuple patterns. So as I said, we use a kind of patterns to represent the relation among sequences. So this represents the append relation. And this is a reverse append. And we also allow conjunction of patterns. So this means that the first element is a prefix of the third one, and the second is a suffix of the third one. Okay? And this has been inspired by Anglin's pattern languages, which are known to be learnable from only positive samples. And we came up with a very simple algorithm to infer such patterns from few positive samples. So here is sample data. And we first look at this red part. And so this coincides with x. So we simplify the data by removing that common part like this. Okay. Then we can see that this red part again coincides with y prime, so that we further simplify the data by removing that part. And then by following these steps, we can see that xy can be represented in this form. Okay? And this says that x is a prefix of y, and the remaining part y prime is again a prefix of x. Here's another example. So this red part of z coincides with the reverse of x. Okay? So we again simplify the data by removing that part. And then we now see that y and z prime coincides. so that we can further simplify the data by removing that part. Okay? And then by following these steps, we can see that x, y, z are in the reverse append relation. Okay. So this algorithm is quite efficient. So since the size of data decreases monotonically, the number of steps is linear in the data, the size of data. Okay. So to characterize the class of patterns inferred by our algorithm, we introduce a notion of solvability. So in the previous slide, I have simplified the data by finding common part of the data and removing them. And here, instead, we simplify the patterns by finding a common part of the patterns and removing them. And then a tuple pattern T is solvable if it can be simplified to a trivial pattern consisting of independent variables. Okay. So for example, this singleton pattern is not solvable because it cannot be simplified further. But this is solvable because it can be simplified to trivial pattern consisting of x and y. Okay? And it turns out that this provides a sound and complete characterization of our algorithm. So the tuple pattern T may be inferred from M if and only if T is a minimal solvable tuple patterns that matches data M. And furthermore, so our algorithm is non-deterministic, but for any solvable tuple pattern, there exists a sort of characteristic data of small size that uniquely identifies the pattern. For example, in the case of this reverse append, these two data are sufficient. Okay. And based on these properties, we can show that the class of solvable tuple patterns are learnable from only positive samples in the sense of Gould's learning model. So in Gould's learning model, for a target language L, we are given enumerations of positive samples. And then we have to make a guess each time a positive sample is given. And then language L is identifiable in the limit if this guess eventually converges to L, like this. Okay. And then it turns out that both the classes of solvable tuple patterns and conjunctive STPs are learnable in this sense. And our algorithm serves as an algorithm to make this guess. And for the purpose of automated verification, actually, Gould's learning model is not sufficient. We need an algorithm to learn inductive invariants. So for a transition system, invariant should satisfy the following two properties. So invariant should contain all the initial states, and invariant should be closed under the transition relation. And assuming that the set of initial states and the transition relation are both described by quantifier-free formulas consisting of word equations, actually we can compute the least or strongest inductive invariant that can be described by conjunctive STPs. And in the case of non-conjunctive STPs, there is no guarantee that strongest invariant exists, but we can enumerate all the minimal STP describable inductive invariants. Okay. And that is important for the application to automated verification. I will explain later. Okay. And this table shows learnability and the complexity of some decision problems. So Anglin's original pattern languages are learnable from only positive samples. But as this table shows, from a computational point of view, it is interactable. So even the inclusion relation is undecidable. in contrast, thanks to the restriction to solvability, our STPs have much better algorithmic properties. In particular, the satisfiability of quantifier formulas given like this is decidable. And that is important for computing inductive invariance explained in the previous slide. And it actually belongs to P space. And that is by reduction to earlier deep results on word equations. Okay, so now let me explain how the theory of solvable tuple patterns can be applied to automated verification. Okay. So let's come back to the original motivating example. Okay. So we wanted to show that this assertion never fails. Okay. So we can reduce this problem to CHC solving problem of checking whether there exists a predicate rev A that satisfies all these clauses. Okay. So here, intuitively, rev A captures the input and output relation of the rev A function. Okay. And the first two clauses correspond to the definition of rev A function. And this goal clause corresponds to the assertion. And actually, in this case, this CHC is satisfiable. And it indeed has this model. So this essentially means that rev A returns the reverse append. Okay. And so the question is how to find this model. And we can use our STP inference for that purpose. So to check the satisfiability of these clauses, we first compute the strongest predicate that satisfies the first two clauses, and then checks whether that satisfies this goal clause. Okay? So that we start with the strongest possible predicate, that is empty set. Okay? And then this obviously does not satisfy the first clause, and we get a counterexample like this one. And then by running STP inference, we get this trivial pattern. Okay? But of course, this does not satisfy the first clause, and we get another counterexample. Okay? And then given these two examples, we obtain a little more general pattern like this. And this satisfies the first clause, but not the second one. So we get another counterexample like this. Then we run STP inference again and obtain this one. But this does not satisfy the second clause either. So we add another counterexample. And at this point, we get this one. And so this represents the reverse append relation. And now we can see that this satisfies all the clauses. So we are done. So that means the original program does not suffer from assertion failures. Okay? And this is not without luck. So in general, this kind of thing is always possible. So for any CHCs over words, both whether it has a STP model and whether it has a CSTP model are decidable. And this is in contrast with the undesirability of the existence of a general arbitrary model, not restricted to STPs. And actually, we can also consider merge set and set versions of solvable tuple patterns. And the same results hold for those variants. Okay. And STP inference alone is often not sufficient in the actual verification. For example, in this case, the function take returns the first n elements of L, and drop removes the first n elements of L. And this main function asserts that the original list can be recovered by appending the outputs of take and drop. Okay? So for this one, our STP inference only informs us that take returns a prefix of L and drop returns a suffix of L. And that is not sufficient for proving this assertion. Okay? But we can strengthen this invariant by combining it with arithmetic reasoning. More specifically, we can apply length abstraction to the program, and by invoking CHC solvers for integers, we get this kind of invariant, and by combining them, we get inductive invariant that is strong enough to show that this assertion always holds. Okay. So we have implemented a new CH solvers for list-like data structures called Shokol, and here is the experimental results. So these are results of performance of our tools, and it significantly outperforms existing tools. Okay, so let me discuss some related work. So our work has been inspired by pattern languages that are learnable from only positive samples. But as I said, STPs have much better algorithmic properties that is important for applications to verification. And there are other data-driven approaches to invariant inference, but they were mostly for inference of numerical relations. And there are other methods for solving CHCs over ADTs, and that are complementary to our technique. But they tend to require heuristics or struggle to prove the equality of lists. So let me conclude. So we have proposed solvable tuple patterns for lightweight inference of relations among sequences. And that has been inspired by pattern languages and word languages. They are earlier deep results. And we have applied STPs to automated program verification. And future work includes the support of more patterns and finding applications other than program verification. Okay, that's it. Thank you for your attention.
Okay, we have time for a couple questions. Could you say a little bit more about the future work? So how would you extend it to map, filter, fold, and trees? That seems like a big jump.
So for trees, actually, naive extension is easy. Maybe I can show you some slides. So we can exploit the similarity between structures. So basically, so in our papers, we have worked on sequences and also multiset and sets. And those are free monoid with some commutativity or idempotency. And in the case of trees, we can just remove the associativity. And yeah, that's an abstract reason why we should be able to extend our framework to cover that one. And fold and map is a bit different, but we have in mind some ad hoc adaptations to deal with that.
Okay, thank you.
Nice talk and nice result. I wanted to ask you about you mentioned word equations being used, like reduction to word equations. I'm just curious if, is it word equations purely, or is it word equations with regular constraints?
Not without regular constraints.
Without?
Pure word equations.
Pure, okay.
Yeah.
Do you think there is an application of adding regular constraints into your sort of analysis framework?
Yeah, of course. So if we also infer some regular language constraints from other means, then we need to decide the word equations with regular constraints. Yeah.
Mm.
All right, let's thank the speaker again. All right, our next speaker is just getting set up now. The next talk will be an efficient algorithm for streaming BPE tokenization. The authors are Konstantinos Mamouros, Angela Lee, and Yudi Yang. And Konstantinos will be giving the talk.
All right, thank you for the introduction. So I will start with an informal definition. Tokenization is the process of splitting text into smaller units that are called tokens. This text can be source code, or natural language, or markup, or some other form of semi-structured data. In the familiar context of compilers, tokenization is the main task in the lexical analysis phase. In that setting, a tokenizer is specified usually using a list of regular expressions. However, this talk is not about tokenization based on regular expressions. Instead, our work is about tokenization using byte pair encoding, or BPE. BPE was introduced as a lossless compression algorithm, and it was later adapted in the context of neural machine translation to segment words in smaller subword units. Today, BPE and its numerous variants are used in LLMs, including the popular GPT and Llama models. Let's see how BPE tokenization is typically used. First, the raw input text is split into tokens, and then each token is mapped to a token identifier, which is an integer. Next, each token identifier is transformed into a high-dimensional vector called a token embedding. And finally, this sequence of high-dimensional vector embeddings are fed as input to the neural architecture. The term BPE tokenization typically refers to the first stage, or sometimes the first two stages of this pipeline. Now, I will describe how a BPE tokenizer is specified by showing a simple example. The first component of the specification is an ordered alphabet of basic symbols, and the second component is an ordered set or list of merge rules. In this talk, I will use the non-standard term BPE rule set to refer to this specification of a BPE tokenizer. Every basic symbol is taken to be a token. Moreover, every merge rule defines a new token by concatenating two previously defined tokens. So a BPE rule set gives rise to a vocabulary of tokens, and each token in this vocabulary is assigned a unique token ID. A BPE rule set is typically obtained through a training process. The rules are learned from a training corpus, and the training procedure takes as input the number k of merge rules to be learned. In practice, k typically ranges from 50,000 to 300,000 rules. In a BPE rule set, a rule that appears earlier in the list is considered to be of higher priority than a rule that appears later. Now, I am ready to describe the procedure that defines BPE tokenization. First, we split the input text into individual basic symbols. The main loop of the procedure repeats as long as there is an applicable merge rule. In every iteration, we first choose the highest priority applicable rule, and then we replace the leftmost occurrence of the token pair of the rule with the token that appears on the right-hand side of the rule. when the loop terminates, the resulting token sequence is the BP tokenization of the input text. Let's look at an example to understand how this procedure works. Suppose that the input text is the word there, T-H-E-R-E. We start by splitting the input into 5 individual basic symbols. Now we notice that there are 4 applicable merge rules. The highest priority rule is the one that merges the token T with the token H. We apply this rule and we obtain this 4-token sequence. Now there are 3 applicable merge rules. The highest priority one is the rule that merges the token TH with the token E. We apply the rule and obtain this 3-token sequence. Now we have 2 merge rules that apply. The highest priority one is the rule that merges the token R with the token E. And after we apply this rule, we obtain this 2-token sequence. At this point, we observe that there is no rule that applies, therefore the procedure terminates. And the highlighted 2-token sequence is the BP tokenization of there. This table shows some existing algorithms and tools for BP tokenization. TickToken is an implementation of this standard BP tokenization procedure that I just described. It has complexity quadratic in n, where n is the length of the input text. Hugging Face uses a priority queue to efficiently identify the leftmost occurrence of the highest priority merge rule that applies. Its complexity is big O of n log n. And finally, DP is a recently proposed algorithm that uses dynamic programming to compute the BP tokenization of every prefix of the input. It has linear complexity. All of these algorithms and tools are non-streaming. Our work, however, focuses on providing fast and low memory streaming BP tokenization. For our approach, we start by defining a BP transducer to be a sequential transducer where both the input and the output alphabets are subsets of the vocabulary of tokens. The first observation is that every merge rule can be described by a BP transducer. Let's look as an example the BP transducer for the rule that merges the token T with the token H. We denote this transducer by A sub TH. The input alphabet consists of the tokens E, H, R, and T, and the output alphabet consists of the tokens E, H, R, T, and TH. This is the diagram for the rule transducer A sub TH. I will not describe this whole graph. I will just describe one path through the automaton. So suppose that we start at the state Q0, which is the initial state, and we receive the input token T. We transition to the state Q1 without emitting any output token. Then suppose that we receive the token H. At this point, we transition to the initial state Q0 and we emit the token TH. Now let us see how we can define a transducer for an entire BP rule set G. We have already discussed how to construct a BP transducer for each individual merge rule. Let's recall the serial composition operation that feeds the output of one transducer as input for another transducer. The main observation is that BP tokenization with the rule set G can be given by the serial composition of all the rule transducers in order of priority. We call this the BP transducer for G, and we denote it by A sub G. a consequence of this is that BP tokenization is a sequential transduction. The operation of serial composition on transducers is a product construction, and for this reason, the transducer A sub G can grow very large. In practice, we have seen that the transducer for fewer than 1,000 rules needs several gigabytes of memory to represent. This means that we cannot construct a monolithic transducer for a real BPE rule set whose size ranges from 50,000 to 300,000 rules. Given this barrier, how can we use BPE transducers to enable streaming BPE tokenization? First, let me define the concept of real length of a token sequence X. This is the length of the concatenation of the tokens inside the sequence X. Now we can define the delay of a BPE transducer A, denoted as delay of A, to be the maximum difference of the real length of a stream prefix X and the real length of the output of A on X. We also define the delay of a BPE rule set G, and we denote this by delay of G to be the delay of the BPE transducer for G. The intuition behind this definition is that the delay of G quantifies the worst case look ahead that is needed before tokens can be safely emitted. Now suppose that capital D is an upper bound on delay of G. Our main theorem says that we can perform streaming BPE tokenization by reading the input as a stream of blocks where each block has size proportional to D. Notice that D only depends on the rule set. For this reason, the size of each block is independent of the length n of the input stream. From this, it easily follows that the time complexity of this procedure is linear in n. The intuition for this theorem is that we can tokenize each block individually using any offline algorithm. The upper bound D ensures that a prefix of the computed token sequence is safe to emit as output. The challenge here is that a precise computation of the quantity delay of G from the BPE transducer A sub G is infeasible because A sub G is too large to construct. So how do we solve this barrier? Our approach relies on the lemma that you see on the slide, and the idea is to group the rules of G in small rule batches and compute the delay for each batch separately. Here is the definition of the BPE transducer for G, where the parentheses in the expression indicate the rule batches. So we construct the transducer for the first batch, the transducer for the second batch, and so on. Now we calculate a delay estimate, capital D, that is the sum of the delays of the batch transducers. This delay estimate is an upper bound on the actual delay of G. For a BPE rule set that consists of 200,000 rules, we have computed a delay estimate D that is less than 3,000. This implies in particular that the memory footprint of our algorithm for streaming BPE tokenization is in the order of just kilobytes. In this plot, we show an experimental comparison of tick token and the Hugging Face tokenizer. The horizontal axis of the plot is the length of the input text in thousands of bytes, and the vertical axis is the throughput in millions of bytes per second. First, we see that the throughput of the Hugging Face tokenizer decreases slowly. On the other hand, the throughput of tick token drops rapidly. The main takeaway here is that tick token is too slow on large inputs. For this reason, we have chosen to exclude tick token from our experiments on larger inputs. In this plot, we see a comparison of our own tool, which we call FST. This just stands for finite state transducer. And our tool is compared against the Hugging Face tokenizer and DP. The main observation in the plot is that both DP and FST have more or less constant throughput as the input length increases, which means that both tools scale pretty well. We also notice that FST is consistently faster than both Hugging Face and DP. Now, let me conclude with a summary of the main points of this work. First of all, our work views BPE tokenization from the lens of sequential transductions. First, we introduced the notion of delay for BPE rule sets. This is a notion that quantifies the worst-case look-ahead that is needed before tokens can be safely emitted in a streaming setting. We show that bounding the delay of a BPE rule set enables streaming BPE tokenization, and we also propose a streaming BPE tokenization algorithm that has time complexity that is linear in n, the length of the input stream, and also has a small memory footprint that is independent of the stream length. Finally, we have shown experimentally that our algorithm performs well against widely used BPE tokenizers, including tick token and the Hugging Face tokenizer. This concludes my talk. Thank you for your attention.
All right, we have time for a question or two.
Hi, nice talk. Previously, you mentioned that PPE tokenization can be done by a serial composition of the tokenization rules, right? But maybe after you applied a rule with low priority, another rule with high priority may be valid again, so you can apply it. I wonder if that happens.
That doesn't happen. And what you're describing, it requires proof. There is a lemma that establishes that for all BPE rule sets that are obtained through training, the situation that you described cannot occur.
Okay, so that's a property for the BPE rule itself. Okay.
Yeah, and it requires proof. It's not immediately obvious. So, yeah.
Really cool talk. I was a little surprised when you said the delay was, the estimate of the delay was 3000. Can you compare the delay to the length of the maximum token? Because I would assume the largest token size is related to the length of the longest word, let's say in English.
Yeah, so that's a great question. Actually, there are pathological rule sets where the delay can grow pretty large. So this is something that can be proved. You can create a chaining, so to speak, of rules that will make the delay pretty large. This doesn't occur in real BPE rule sets. So in these pathological cases, delay can be much, much larger than token length.
So it has nothing to do with word length?
So you can show that in the worst case, the delay is bounded above by the sum of the leftmost token in every rule. So if you consider all the rules, look at the leftmost tokens, and you add up those lengths, this forms an upper bound for the delay. And this can actually be tight in some pathological rule sets.
Hi, Max here. I know you're doing streaming tokenization, but it seems like some of the stuff you're doing for delay would also be useful for parallelization of tokenization. Is that something you're looking at all, or anyone's looked at?
Oh, that's a great question. So I don't think that anyone has looked at this, but I mean, what you just said is a great point. So essentially, delay allows you to carve up the input in smaller blocks, and each block can be processed independently of the other. So I think that's an interesting direction for future work. But I don't know if anyone has looked at that.
All right, let's thank the speaker again. All right. Our next talk is scalable floating point satisfiability via staged optimization. The authors are Yuandra Zhang, Zhulei Fu, and Benoit Ravindran. And Yuandra will be giving the talk.
Hi, everyone. Thank you for coming. So it's very nice to see you today. Today, my talk is about scalable floating point certifiability via stage optimization. My name is Yuandra. So floating point arithmetic is actually fundamental to numerical software. It's actually how computers do real number math, but it does not behave like our real number math arithmetic, because floating point arithmetic can include problems like rounding error, non-associativity, and special values. We usually use SMD solvers to formally assert the satisfiability problem. And because these satisfiability problems live in real code, we want to find them automatically. So that comes down to a question, is there an input that makes the program goes wrong? So the insight is that detecting a floating point assertion violation reduced to a floating point satisfiability query. For example, the C code shows how to reach the assertion. We can collect the conditions that lead into the assertion and translate the program path into conjunctive normal form formula on the right. So finding an input that violates the assertion is actually equivalent to solve the formula on the right. So, and SMD solving is usually used as a backend for the symbolic execution. There are actually two ways to solve the satisfiability problem. So one is the most commonly used, called bait blasting approach. It is good for completeness, meaning that it can give set and unset proofs, but it may face exponential blow up on nonlinear constraints. Another approach is called optimization-based approach. It's faster on small formulas, but it cannot give unset proofs. So our work is based on optimization approach. So previous solvers like XSET and Greater transfer constraint satisfiability problem to numerical minimization problem. So given a CNF formula, we can encode it to a non-negative representing function called Rx, and then we call a global minimizer to solve the satisfiability. The key property here is that if an input vector x makes Rx equals 0, then x can satisfy constraint C. So here we show a small toy example. We have two floats, x and y. The constraint is x equals 1.0 and y equals x. So the unique model is 1.0, 1.0. So here we show two ways to build the objective. The first way is through square residuals. It has smooth landscape, and the mathematical minimizer can handle it well, but it suffers from bit level accuracy problem because of the floating point errors. The second way is using a squared ULP distance. So it has staircase-like landscape, so the optimizer finds it hard to minimize, but it ensures bit level correctness. Here we know that the ULP of A and B actually returns how many representative floats between A and B. Here is our overview of our tool, StageSet. So it introduced a new way to construct the objective function through 3-stage pipeline. So the stage 1 used projection-aided square residuals as objective to find a trustworthy basin. And then stage 2 used a square ULP distance as the representing function to ensure the bit level correctness. And finally, the stage 3 used a discrete lattice search to some near misses. And here, our soundness guarantee is that stage 2 and stage 3 are using representing functions. So it will become 0 if and only if when all the constraints are satisfied. Stage 1 actually used the square objective as a starting point. So let's say a C to be a conjunctive normal form of floating point constraints. Here, the big wedge stands for clauses, and the big V stands for literals inside the clauses. Eij and E prime ij are the left-hand side and right-hand side of the ith literal in the JS clause, and the bow tie symbol stands for comparison operators. We then encode this constraint set as a non-negative objective function. So following the sum over conjunction and the product over disjunction scheme. The inner product encodes each disjunction. So if any literal is satisfied, the whole product becomes 0. The outer sum encodes the conjunction. So the total is 0 only when all clauses are satisfied. The per atom distance d measures how far a single atom is from being true. So for equality, it's square residual. For non-strict inequalities, d is 0 when the inequality holds, otherwise square residuals. For strict inequalities, we add a +1 term to ensure boundary case gets a non-zero penalty. For this equality, d is 0 when two sides differ and become 1 when they are equal. Stage 1 splits the constraints into two groups actually. So the first group is called L, which is the top level linear equality constraints, and N is the remaining atoms, including the nonlinear constraints and other linear constraints. For L, instead of using the raw squared residuals, we actually measure the exact geometric distance from input vector x to the linear manifold, plus the sum over other clauses penalties, which are defined in the previous slide. We measure the exact geometric distance through orthogonal projection. The operator pi sub L of x maps x onto the linear manifold by Moore-Penrose pseudo-inverse. The square distance from x to its projection then has a closed form shown on the right. The key idea is that projecting onto the linear manifold gives the exact square distance and removes the distortion that a naive object might introduce. Here we show a small toy example. So consider a toy formula x equals 1.0 and y equals x. The unique model is 1.0, 1.0. The naive objective on the left just sums the square residuals. So the problem is that objective doesn't always agree with the geometry. Like moving from point 2, 2 to 1 brings us actually closer to the model, but the objective increases. The projected objective on the right fixes. So for this toy, the linear manifold actually collapses to a single point, 1, 1. So the S1 of x and y is defined, shown here, and S1 will always decrease aligned with the true distance. And in stage 2, we still use the same scheme, which is sum over conjunction and product over disjunction. But for per atom distance, we replace square residuals with ULP squared distance to ensure bit level correctness. So the objective S2 of x is actually the sum over all clauses phi in the formula C. This construction actually makes x2 a representative function of constraint C, since it's always non-negative and it equals 0 if only if the assignment x satisfies the formula. For stage 3, we actually start from the best assignment that stage 2 returned. So after stage 2 continuous optimization, we use discrete floating point lattice search around x2 star. So the key primitive here is NULP of k and z, which shifts a float z by k ULPs. And S3 objective use S2's exact same structure. The only difference is that instead of changing input vector x, we modify the input integer vector n. Here, a key primitive is NULP of n and x2 star, which means the lattice point you reach by stepping each coordinate of x2 star by the corresponding integer number of ULPs from n. And also, S3 is also a representative function, even at discrete steps. Here we show a toy example to illustrate our stage 3 design intuition. So let's say for a 20 variable chain, which is anchored at a tiny constant, so after stage 2 search, a few coordinates might be off by some ULPs, since S2 continuous steps might overshot at such tiny scales. So after using S3 as a discrete lattice search, the last few bits can be tweaked. So here is our overall procedure. So the first step is to build the 3-stage objective function from constraints CNF formula. The second step, we use a global minimizer on S1. Starting from a multi-star box, it will return the best assignment x1 star. One thing to note is that we don't certify SAT here. The third step is to minimize S2 starting from x1 star. If the resulting minimum V2 equals 0, we certify SAT and return x2 star. If S2 didn't reach 0, we run S3's discrete lattice search around x2 star. So if the minimum V3 equals 0, then we return SAT and return the model. Otherwise, we return on-set guess or timeout if the time budget expired. Here we show our evaluation results. So we actually evaluate our tool on 5 benchmark suits. The first 3 comes from MathSat suits contributed by the MathSat author from SMT Competition 25. We separate them into 3 groups, large, middle, and small, based on its file size. We also use previous work, Greater and GFS benchmark suits. So here we use 2 evaluation metrics. The first metric is called SAT recall, which measures how many truly satisfiable problems that the solver actually finds models for. The second is timeout rate. So it's just the number of benchmarks that has no verdict within the time limit divided by the total number of benchmarks. And the timeout limit is 20 minutes per instance. We mark our tool StageSat in maroon. So StageSat reaches 100% SAT recall on 4 of the 5 benchmark suits. On the biggest and hardest suit, MathSat large, StageSat reaches the highest SAT recall among all the solvers. And StageSat solved 439 of total 443 benchmarks and got 4 timeouts. In MathSat large suit, here is the SAT recall performance for all the evaluated solvers. StageSat solved 45 out of total 49 benchmarks and correctly find 24 satisfiable models, and all on-set guess are aligned with the complete solver's verdicts. And it has 8.2% timeout rate. Here we also show the timeout rate performance in MathSat large suit. One thing that worth note is that XSAT and GoSat actually reaches even lower timeout rate than our tool StageSat, but they sacrifice SAT recall a lot. So StageSat actually has a relatively low timeout rate, but can actually achieve the highest SAT recall among all the solvers. So in conclusion, we introduced StageSat, which is a new SMT solver for floating points constraints. It's based on mathematical optimization approach. And we introduced a 3-stage pipeline for constructing the objective. And we also use orthogonal projection to help improve the descent quality. And in our evaluation, StageSat shows an advantage in handling large formulas compared with other solvers. So that's it. Thank you for listening.
All right, we have time for some questions.
Yeah, very nice piece of work. I had a clarification question. So in your squared objective calculation, is it trying to make a certain constraint system convex? Is that the intuition? You take the distance metric that you showed, 0 equal to x and x equal to y, that example, you have to fix it up. is it sort of making that system a bit convex? Is that what you did there?
Oh yeah, yeah. So we actually, so for the first stage, we use the square objective as you said. And as I mentioned before, so so the minimizer is more performance well on the smooth landscape. So for the ULP, so it's more like a staircase. So the minimizer will, in our evaluation, it will take much more iterations to converge. So we start with a relatively light, I mean, the square objective as a quick search to help us quickly find the trustworthy basin, and then we use some more expensive ULP search later. So yeah, that's our design intuition.
Yeah, I heard a few more quick questions, which is if you have an associative rule like E1 plus E2 plus E3 less than E1 plus E2 plus E3, you know? So it's an associative law that should not hold in the real number system, but in floating point it can. And you need to do deep error analysis into these expressions to know whether to find the set. How do you do error analysis in this framework?
Sorry, can you?
So yeah, you could take the usual A plus B plus C less than A plus B plus C. Now imagine A, B, and C being substituted with complex expressions.
Oh, okay.
Then you have to do deep error analysis to find the satisfying points. How do you do error analysis?
Error analysis?
Yeah, numerical error analysis. Like if you have X plus Y, there is an error introduced, 1 plus delta error model or things like that, numerical error. Do you do numerical error analysis on top of the operators that you use in the constraints, like addition, square root, and all that? That's my basic question. Yeah.
Oh, sorry, I misunderstand. So we don't modify any constraints, so we just given us SMT formula, yeah. So we don't do any further analysis based on the constraints.
Put an error box around it. That's what I was thinking. Okay, thanks.
Yeah, sorry.
Yeah, very great results. I'm wondering whether I can use stage set for real number constraints, or it's floating point constraints only.
It's only used for floating point constraints.
Okay, got it. Thank you.
All right, let's thank the speaker again.
Sorry, I think I have to. Yeah, I'll just do present. Oh my God. Can you hear me okay? Yeah.
All right, so our next talk is on EREQ, regular expressions with quantifiers and incremental quantifier elimination by Ekaterina Zhuchko, Ian Varatalu, Margus Wiens, and Nikolai Bjorner. And Ekaterina will be giving the talk.
Thank you. So you introduced us all already. Let me start with the motivating example for this work, which is learning specifications from traces of a cloud storage service. A trace in this context is a word over an alphabet of actions. In a simplified setting, these can be things like updating an object or deleting or undeleting it. The things that we want to learn can come in different shapes as well. For example, enabling conditions. something of the form delete enables undelete. So undelete can only occur after delete has already occurred. Now, this condition is naturally expressed as a first-order logic formula. For all positions in the trace, if undelete has occurred, it means that previously, at some point in the trace, delete has occurred. Similarly, we would like to express disabling conditions. So for example, delete disables next delete, which means delete cannot occur twice in a row. Now, this thing is more naturally expressed as a regular expression of this form, where the body says match anything, then we have a sequence of 2 deletes, and then anything again. And this pattern should not occur. So the key observation here is that different types of conditions require a different notation of formalism. So the question is, can we have one language which supports both of them? The answer is, of course, yes, and this is what this talk is about. EREQ allows us to switch between the two, or more like it has both of these formalisms, so you can use quantifiers when necessary or regexes when it's more natural. One thing is that regular expressions cannot express position-dependent properties. So where do we get the quantifiers from? We start with weak monadic second-order logic, which does have quantifiers, and the variables range over positions in a word or finite sets of positions. Now, the atomic formulas come of several shapes. So we have predicates, which assert that at a certain position a label holds. We have order and subset relations, and we also have a singleton construct, which allows us to essentially eliminate talking about first-order variables. Now, there is a celebrated result, which says that weak MSO has the same expressivity as regular languages. Now, the small caveat is that the corresponding decision procedure has non-elementary complexity. Nonetheless, almost 30 years ago, some researchers in Aarhus developed a weak MSO solver, which was actually practical. There's some really clever engineering. So despite this horrible worst case, they were able to solve practical problems. And it's still the state of the art today. Let's now look at the decision procedure, so the classical approach, which is also taken by Mona. We start with a weak MSO formula. We translate it to a finite state automaton. And then we check emptiness, which corresponds precisely to check and satisfiability of the formula. Now, to explain the cost of this construction, let's consider the formula not exists X, such as phi. This approach builds the automaton from the innermost formula. So we start with the automaton for phi. Then we have to deal with the quantifier, which introduces non-determinism because it corresponds to projection. And then we have a complement. So we are forced to determinize. And this is where the exponential cost comes from. Now, if you imagine a more complicated formula with several quantifier alternations, each one of them essentially adds an additional exponential cost. And this is where the non-elementary complexity comes from. We have a tower of exponentials, which is stemming from these quantifier alternations in the formula. And now the question is, can we avoid constructing the automaton explicitly? In our work, we instead translate the weak MSO formulas into EREQ. And then our decision procedure is based on symbolic derivatives. So we lazily explore the state space and then check if some state is nullable, meaning the empty word is in the language of that state. And what does it give us? Well, it's a lazy top-down exploration using symbolic derivatives as opposed to the bottom-up approach taken in the classical decision procedure. And then this way, we avoid explicit automata construction, which is what we wanted to do. So let me introduce EREQ and the corresponding decision procedure. So really, EREQ is a conservative extension of ERE. So the new operator is the existential quantifier. One thing worth mentioning is that is non-standard. Instead of concrete characters, we are working modulo an alphabet theory, so we have a set of predicates. And these predicates come of two different shapes. One of them is the lowercase alpha. You can intuitively think as character predicates. So you can think about, I don't know, digit, or lowercase, uppercase letters. Whereas the PIs are an artifact of introducing the quantifiers, and I will explain a bit more on the next slide. The universal quantifier is just syntactic sugar defined in the usual way. And then the interesting part is that the semantics of the existential quantifier require us to extend the alphabet. So let me explain what I mean by that. So we take our alphabet sigma and we extend it with bit vectors of size n, where n corresponds to the number of free variables in the corresponding formula. Let's look at a concrete example. So we have a word BBAB, and then we have two variable assignments. So there's two free variables in the formula. And now the extended word is of the following shape. So we have this table where the first row is just the character component in the usual way. Oh, sorry, I had highlighters, but they do not show up. So I'm going to try to use this. So the first assignment tells us that the positions that are active are positions 2 and 3. So the first row marks precisely those positions. The rest of them are false. Similarly, the second assignment tells us that there is 3 active positions, 0, 1, and 4. So the last row marks precisely those positions, and the rest of them are false. So in that way, we're able to map the variable assignments into the words. And now the role of the two different types of predicates are clear because we have the character component and then we have the propositional component, which is a way to encode the assignments. So with this, we can define the semantics of the existential quantifier. We're using projection here, but the idea is that we project away one of the quantified bits. So essentially, we just remove the row of all the words in the language, going from n+1 variables to n. So for the translation, the Boolean operators and the existential are quite straightforward. They just map to the corresponding counterparts in EREQ. The more interesting part is the atomic formulas. So let's look at the first constructor. So the VKMSO formula is telling us that so xi is just a second order variable, and there is some position that has the label alpha. And now, in order to translate it to a regex, we are taking advantage of the two types of predicates. What we're saying is that the regex is matching anything, and then at some point, we would like to state that both the alpha component and the propositional component are true at a certain position in the word. And then again, we don't care what happens after. So similarly, in the other cases, we are just using the predicates in order to encode the constraints from VKMSO formulas into the regexes. And then we formally prove that the translation is correct. So if a word is in the language of the formula, then the encoded word is also in the language of the translated formula. I mentioned that the key ingredient of our decision procedure is symbolic derivatives. So you may have heard of Berzovsky derivative, which is an old concept. So the derivative of a regex with respect to a single character is just all the continuations after reading this character C. In our context, a symbolic derivative of a regex is a term tree. So instead of encoding it character by character, we encode all one-step transitions in a single symbolic step. So here I have an example for the base predicate, the symbolic derivative of some alpha is a tree where the node contains the predicate, and we have two leaves. One is epsilon, one is bottom. And the idea is that you can later evaluate this tree with a concrete character, and depending whether the character matches the condition, you either go left or right, and you end up in two different states. We show that this definition respects the semantics, and here the idea is that if you take the symbolic derivative over regex and then evaluate it on a concrete character, what you get is essentially the classical definition, except now we can replace many concrete steps with one symbolic one. And this symbolic structure is exactly what enables us to introduce a new rule for the quantifier. The idea with derivatives is that we want to have nice algebraic rules, and since we extended with the existential quantifier, we want to keep that. So what we managed to achieve with this is that derivatives also distribute over the quantifiers. Of course, with the universal quantifier, it's just a consequence of the fact that complement and the existential individually distribute. So it's a combination of those. But what this means is that we can eliminate the quantifiers incrementally during construction with the derivative. So remember before, with the classical procedure, we were forced to determinize. But here, we can have the incrementality that we wanted. And the idea is that we don't need to construct the full automaton up front. Another thing is we have some nice algebraic laws. So the existential distributes over concatenation, the Kleene star, and disjunction. And the reason why it's interesting is because we can eagerly do rewrites during construction and, again, simplify the expressions, trying to prune the state space as much as possible. So now we have all the ingredients for the decision procedure. We start with the weak MSO formula. We use the translation that I showed earlier. And then we unfold the symbolic derivatives, exploring all the reachable states and checking nullability. So if we reach such a state, then we get the satisfiability of the original formula. Now, one important question here is, does this procedure terminate? And what this really depends on is whether the derivative closure is finite. And indeed it is. We, again, formally prove this result. So now all the theory is in place. Let's look at some evaluation of how this performs in practice. We have implemented the solver in Rust. And first, I will demonstrate the evaluation on random benchmarks. So compared to Mona, as I say, this is state of the art. It's no surprise that Mona still leads overall. I mean, we're competing with 30 years of optimizations. But EREQ is still competitive on the 10,000 benchmarks that we tested on. And one interesting thing, as you can see, there is two blue curves for EREQ. The lower one is essentially choosing the best configurations amongst all for each benchmark. What I mean by that is we are switching between different normal forms and then choosing the best out of the ones available. This is a new axis of optimization because Mona, in some sense, commits to one normal form at the beginning, whereas we are able to exploit several normal forms, for example, negation normal form, CNF, DNF, or anti-prenex normal form, and then utilize the best one. But really, the more interesting set of benchmarks is the structured benchmarks. So we have several families, including counter, which encodes binary addition problems, and lift problems, which is essentially a specification of an elevator system with the parameter n corresponding to the number of floors in this system. So EREQ solves all 50 problems, whereas Mona solves 30 out of them. And the ones that Mona cannot solve are precisely these counter and lift problems beyond a certain bound. So the two solvers have different failure modes. For Mona, it essentially hits a space wall, whether it's the limit on the BDD nodes or out of memory. For EREQ, we hit the time wall with the 60-second timeout. Now, one of the things we haven't utilized yet is understanding which of the normal forms is best. At the moment, it's kind of a future work to experiment and really take advantage of this, axis of optimization. So we believe that there is a lot of more work that can be done in order to bring us closer to Mona on the, for example, random set of benchmarks. Okay, so in summary, we introduce extended regular expressions with quantifiers, which have the same expressiveness as weak MSO, with a linear time translation. The key insight that we have is that the derivative distributes over quantifiers, and we can incrementally eliminate the quantifiers during construction. All the core theory has been verified in Lean, and we have a prototype solver in Rust, which has competitive performance with Mona, especially on the structured families of benchmarks. And as for future work, we would like to revisit many of the applications that Mona introduced, including things like protocol verification. And also, one thing that's missing from the current benchmarks is the regex fragment of EREQ is not really tested. I mean, concatenation, star, and the modulo theory aspect. And as I mentioned, we would like to investigate the different search strategies and how to utilize them in the future. Thank you, and I'll take any questions.
All right, we have time for a question or two.
Hi, great talk. Tom Ball, University of Washington. So what data structures are you using? Are you using BDDs or anything?
Yeah, we're also, yeah, exactly. We're also using BDDs to represent, well, both the predicates and the transition term themselves are sort of like multi-terminal BDDs. So we have like two layers of BDDs, you could say, for the predicates and for the transition terms.
So the fact that you're not getting the space outs, but is the fact that you're doing things lazily. You're not using, like Mona is using them much more aggressively because they're representing the eagerly constructed automata, and there's just many more nodes in the BDD?
Yeah, exactly. Okay. And yeah.
Hi, Cass Alexandru, RPTU Kaiserslautern. I wanted to ask, so essentially this derivative sort of, you can think of it as walking through like an automaton that isn't fully constructed, right? In some sense.
Yes. Oh, let me be also upfront here. So in the cases where the problems are unsatisfiable, I mean, we cannot avoid the worst case, right? We may be still exploring the entirety of the state space. What we can do is aggressively prune it on the fly through like rewrite rules, for example. Yeah.
What I wanted to ask was, so I don't know about how Mona is implemented, but would it theoretically be possible to have like a solver that constructs like the determinized automaton, but in a way that it does it lazily, and then that sort of the evaluation of like a path of a trace in that automaton would correspond to this symbolic derivative, or is that not possible? Because you said there's this bottom-up thing going on. So is it like, do you have to build the entire automaton?
In the case of Mona, yes. I know some people have explored other methods, but I'm most familiar with Mona, where they just have to explicitly construct the automaton and determinize, they minimize the automaton quite frequently. So that, yeah, you cannot escape this in their setup. But I'm not sure if in general, maybe you can do some clever tricks to avoid it. Yeah.
Because I'd just be curious if it would be like technically possible if you don't construct like the sort of the data structure completely upfront, whether sort of a path through that data structure and the lazy construction of the data structure would be the same or like equivalent to this derivative. But anyway.
Yeah, please.
How does this work? Okay. So I would like to comment on this. The core issue is classical techniques do not allow you to propagate complement. So you have a fixed finite alphabet, you have to construct the automaton explicitly, then do the power set construction explicitly, and then you can determinize. The fact that you're using derivatives with symbolic predicates allows you to propagate complement over the two branches. You cannot do that with a classical finite alphabet. It just makes no sense. You have to have an if then else case where you can just apply this rule. So that's the difference. Yeah.
All right, let's thank the speaker again.
All right, I'm assuming we'll get more people filtering in from lunch as we go, but just to keep things on time, let's get started. Welcome back to this session on generative testing and program synthesis. And for the first talk, we have Michael Gu from University of Washington.
Hello? Hello. Okay. Hi, everyone. I'm Michael. I'm a third-year PhD student from University of Washington, advised by Barish Khashoggi. I'm very glad to present Pathfinder, scalable and accurate application-level crash consistency testing via representative testing. This is joint work with the University of California, Santa Cruz, University of Michigan, and University of Washington. This is a paper published at Uppsala 2025. We didn't get to present it due to travel reasons. And thanks again for the PLDI conference, as well as Splash, to give us this unique opportunity to present it here. Cool. So first, just a little bit of the context of what problem we're solving. Crash consistency refers to an application's ability to maintain a consistent state of data in the presence of an unexpected crash. So applications with data persistent needs, like databases, storage engines, they interact with the storage through POSIX interface or through MMIO, memory map IO. Just to give example, here's just a little example of POSIX-based applications. It interacts with the file system through issuing these write calls. So and here is like 3 write calls, 2 to this log file 1, and another 1 to log file 2. In another way, you can also do such update and persist it through the memory map IO. So for example, here is a MMIO-based application which issues 3 stores, 2 to this variable x, and another store to this variable y. However, for performance benefits, the underlying file system may buffer updates in memory without application developers to issue explicit like synchronization calls or ordering calls like fsync to flush the data to the disk. The order at which the data is persisted is actually unknown a priori. So if we take a look at example here, although the issue order is like this, actually the persisted order may be reordered. So for example, the third write to this log file 2 may be reordered before the second write to log file 1. Similar thing could happen for MMIO-based application. The third store to this variable y may be reordered before the second store to variable x. Consequently, the crash state space will actually grow exponentially as the number of operations increases. If we consider there is a crash happening, an unpleasant crash, during the middle of these 2 applications, if we reason about the possible crash states, we'll find out that both of these applications actually would have 6 possible crash states when there's such crash. Either there's no any operations persisted, only operation 3 or operation 1 is persisted, or operation 1 and 2, operation 1 and operation 3 are persisted, or in the end, all the operations are persisted. So you can see this size of the crash state will quickly grow as the number of operations increases. And the key question we try to ask is, how do we perform crash consistency testing efficiently? Okay, now we're not the first group, of course, to think about dealing with this problem. And prior works have taken majority like 2 primary approaches to test crash consistency bugs. One of them is model checking, which actually exhaustively create all the possible crash states from a given execution or set of executions and test them for correctness, additionally using partial order reductions techniques to avoid generating equivalent states multiple times. So these kind of works are extremely thorough. However, they struggle to scale to testing production-ready systems, as production-ready systems with realistic workloads will generate too many unique states to be actually tested within a given time constraint. Another class of work is actually pattern-based approaches. What they do is actually they prune the state space that needs to be tested and only test those crash states are more likely to contain bugs based on study of non-bugs in the non-applications. The good thing is these approaches will scale well. However, they're prone to miss many bugs, particularly when such bugs do not match the pattern of these non-applications. So in this work, we try to basically see this trade-off between scalability and accuracy in crash consistency bug detection. And the goal of our work is to therefore try to explore alternative approaches that could actually get us the best of both worlds. So both scalable as well as accurate. Our key insight is actually what we call state equivalence, is that the program can generate a wide variety of non-identical crash states that actually ultimately they expose the same crash consistency bug. I'll explain in a second, but we call this state equivalent in the context of crash consistency testing. Let's consider the following example of an entry structure in a hash table that is backed by an MMIO file. The insert function would create a new entry and modify the key value and the valid flag. We can see that this update is supposed to be atomic because if you take a look at the check consistency function, which tests if the valid flag is true, the key value should both be initialized, as we can see from line 19 here. However, these updates have no ordering enforced between them. So if a crash occurs, it is possible that it will generate a crash state that actually has the valid bit set to true without the key and value being initialized properly. And also, this is not the only place where such crash consistency bug can occur. Consider there's another replace function where actually replace the value of an existing key by creating a new entry with the old key and a new value and set the valid flag. And then it actually invalidate the old entry. This function also attempts to perform atomic update, but suffers from the same crash consistency bug as the insert function, as the valid bit is actually not ordered with respect to the key and value updates. So in the sense that actually these functions suffer from the same crash consistency violation, right, at this check consistent function, we can say that the crash states generated by these functions are in fact equivalent. Is this actually a much broader equivalence relation than what actually has been tested many times using this dynamic partial order reduction works in the past? Which they actually required equivalence as having actual identical crash states or identical recovery executions, which is not the case that we see here. Now the problem is, if you actually want to conclusively find all of these states, we need to actually exhaustively test all the crash states, and such that then we can find the smallest subset that expose all of these possible bugs, which actually would be computationally intractable. So our new question becomes, actually, is there any way we can leverage this insight to more efficiently prune the crash state space, even if we have to approximate this minimal set of crash states that we want to test? We observe that applications perform semantically related updates with actually high temporal locality. This is what we call update behaviors in the programs. In our previous example, both functions created equivalent crash states due to the modifications made to the entry structure within confines of the single function. We can see that again in the insert function, where the three updates can actually cause a violation in the check consistency function shown above that occur solely within the insert function. And this function is designed to perform a single semantically meaningful update to actually the data structure of this entry, right? And now we have a couple of different behaviors that can demonstrate the same crash consistency bugs. Which one we actually would like to test? Do we test the insert function, or do we actually test the replace function? Our final observation here is that even though these different behaviors can produce some equivalent crash states, they may not create the same number of crash states. If one set of updates produce a, let's call, superset of crash states, for example, it may update more fields than the previous one, it can actually represent many other updates. For example, if we consider this insert order function here, which actually ensures that the key field is updated and persisted before other fields, but the value field, the value field and also the valid bit may still be reordered, This still results in triggering, of course, one of the assertion failures in the check consistency function. However, due to the added ordering constraint, the crashes during the insert ordering function would generate fewer possible crash states, and therefore fewer possible crash consistency bugs by definition, right? And this means that we actually just need to test the original insert function instead of the insert order function. And this will result in finding more unique crash consistency bugs. And in this way, we say that the behavior in the insert function above is actually representing the insert ordered function below. I want to also note that this approximation is not sound, but it can actually potentially miss bugs. It will ultimately result in far more test state being pruned over the sound approaches and still provide a practical way to find many crash consistency bugs as we evaluated. So overall, we observed that we can provide more thorough crash state pruning by finding and testing representative update behaviors, as testing them should expose just as many crash consistency bugs as testing all of the behaviors. With this insight leads us to build Pathfinder, which is actually a trace-based tool to find and subsequently test all of the representative update behaviors for the crash consistency testing. So Pathfinder first traces operations of applications at runtime to collect a set of operations to analyze. It supports both MMIO and POSIX applications, and then construct a persistent graph. The persistent graph will represent operations as nodes and what happened before persistent dependencies between operations as edges. This graph encodes all the ways a program update could occur in the system, and more importantly, how updates may or may not be persisted if a crash were to occur at given times. So for POSIX, we support tracing the syscall trace using the file system persistent model you want to use, exe4 or any cloud file system, as long as you can express them. And for the MMIO-based applications, we support memory trace as well as memory persistent models. In this way, we use the persistent x84 model, but you can also modify if you need to test other behaviors in your application. Pathfinder then used the update behavior-based heuristic to break the graph into smaller graphs, which represent the ordering constraints to which the approximate the update behaviors that developers would use to perform individual updates. So for POSIX, Pathfinder create update behaviors by from functions, by grouping functions. And Pathfinder use actually a backtrace provided in the function to derive update behaviors, and they group them by traversing the call stack tree. For MMIO, on the other side, Pathfinder creates update behaviors actually by looking at data structures. It employs heuristic approach to determine if an MMIO operation are related or semantically related based on the data type of the instance modified, as well as the temporal locality of these operations. Here, just to give a short example, so for POSIX-based applications, we start from some trace that have these syscall operations, and then we collect the backtrace as the application is running. And then you can see here, the entry function is function 1, and it calls subroutine function 2, function 3, and function 3 calls 2 subroutine, function 4 and 5. So what we do in Pathfinder is that we first group by the leaf nodes, so that it start by grouping the leaf functions subroutines like function 2, function 4, and function 5. And then since we have the knowledge of this call stack tree, we build this call stack tree from the backtrace, we can actually group the functions level by level. So let's say we want to group the parent function, function 3. That basically would just be grouping all the operations invoked by function 4 and 5, and so on and so forth. And then basically, this will create subgraphs that you want to test, and the subgraph can get bigger and bigger as you move from the leaf functions to the parent functions. For MMIO-based applications, the heuristic we use actually are two main splitting criteria. First is if there's previous updates to some field in this data structure M, while the previous updates to M has already been persisted. This typically means like, okay, for example, in a loop, you're updating this data structure, you're persisting at each iteration. Or if there's an update to a different instance N, where the previous updates to M has already been persisted. This typically indicates that the current modification to this data structure of this field n has been completed, and you're updating something else that are semantically not related to n. So just to give you an example, let's say we have this persistent graph that involves the two data structure that is actually updating, structure m and n. And then basically, the splitting criteria 1 would help break epoch 1 and epoch 2, because you see it's updating this field A in structure M again, as like all of the previous updates in epoch 1 has been persisted. And the splitting criteria 2 would help break epoch 2 and 3, because you will see again, there's some updates to data structure N, which is actually not the same one as this M, and also the previous updates to data structure N has already been persisted. So after we group this, after we create these update behaviors, Pathfinder then group these mechanisms together by the most representative behaviors to reduce the amount of testing which needs to be performed. And then actually perform crash consistency testing on the representative update behaviors and generate all the crash data that could result from this update behavior, and then report any crash consistency bugs reported from the testing oracle. And for the representative testing, as I've shown in the example, we group update behaviors following the supergraph, subgraph relationship, and we only test update behaviors that are representative of others. Okay, finally, let's talk about how Pathfinder perform. First and most, we find that Pathfinder is an effective crash consistency testing tool, finding over 120 crash consistency bugs in 22 applications, including finding 56 brand new bugs, which is particularly impressive when given this application we tested has already been rigorously tested in prior works, 102 of them in MMIO micro benchmarks, and 18 of them in production-ready systems. Furthermore, we find that this approach is much more scalable than prior exhaustive testing approach, as well as dynamic partial order reduction approaches. As Pathfinder finds all of these bugs within the 2-hour testing time limit, while other approaches only find a part of them. We also evaluated the effectiveness of our heuristic. And here we're comparing with an exhaustive model checking baseline, which actually try to enumerate all the possible crash states and then do the crash consistency testing. And then we evaluated on the production-ready systems in MMIO and in POSIX. So for MMIO, HSC, Memcached, Redis. For POSIX, mostly database and storage engines. And we can see that Pathfinder is able to find all crash consistency bugs in production-ready system with a crash state reduction from 90% to 99%. Especially for LevelDB and RocksDB, it has very good crash state reduction because they're running these stress testing, which involves like hundreds and thousands of operations, where the exhaustive model checking would just not even scale to that scale. And that's all for my presentation. Thank you for listening. If you have any questions, feel free to let me know.
Questions? So while people are thinking, you had the example of the two different functions where one over-approximates the other. So I get the idea that you're more likely to find a bug if you can prune it down in that way. Mm-hmm. But then you might miss the fact that both of those functions were buggy. Is the idea then that you find the first bug and then fix it and then go back and find that the other function also had bugs?
Mm-hmm. Yeah, that would be typically the workflow indeed, because during the tracing, we first run the workflow and then we produce a trace, and then we reason about all the persistent crash, potential crash consistency bugs in the trace, right? And if there's an oracle actually reports any bug, we have to ask the developer to fix it in order for the workload to run and then discover more bugs. So otherwise, it would just maybe the oracle would just report the failure on the first occurrence. But I think that's generally like maybe a strategy that people would use actually when they're doing testing, because the workload does not need to change, and just fix the bug and then run the workload again to test if there are other potential bugs.
Other questions? You can go ahead and set it. Once, going twice. All right. If there are no other questions, let's thank the speaker again.
Should I try to... It seems doesn't work. Yeah. Oh, I guess it's not to plug in correctly. Okay, I think I'm ready. Yeah, I'm ready.
All right. Our next speaker is Jojo from Purdue.
Yeah. Hello, everyone. My name is Jojo from Purdue University. It's glad to introduce our work, trace-guided synthesis of effectful test generators. This is joint work with Ankush Dase, Benjamin Delaware, and Suresh Jaganathan. Our work is about probability-based testing. Let me first give you some basic intuition. Assume that you want to test a functional program, but you don't want to write down the unit test manually. So you can take a test generator, generate test inputs for you, and you execute the program, gets outputs, and then you combine both of them to what they call the executable property, which define what it means about the functional correctness of the program. If you find a violation, it means that you do detect the bug. Otherwise, you can just do it, retry it, ask the test generator provide another test input, and do that once again. Now the question is that how can we make this whole procedure more efficient? One idea of the probability-based testing is that the test generator need to focus on do some smart exploration, focus on some input space more likely to trigger the potential bug. And that smart exploration needs some guidance provided by the human. For example, if you want to test the insert function, which take a tree and element, then return another tree. The property is if the input tree is a binary search tree, or BST, the output tree should also be a BST. Look at this test input. You will find this tree is not even a BST. So that will be directly rejected by the precondition of the property. So explore this test input is totally useless. Then one kind of guidance provided by the human need to contain some basic correctness to avoid this bad input. Here's another kind of input. We believe that is good because it have somehow smaller depths of the tree. User probably have some domain knowledge that believe a smaller depth of the tree were more likely to trigger the bug. So another kind of guidance is a search bias. However, the things are quite different when you do the PBT with effects. Now we don't have a functional program, but we have an effectful system, just like a stateful library have a shared internal state, and that also provide a set of APIs. So the test generator don't provide a test input, but do interaction with the effectful system. For example, where there's input events and output events. That is some invocation of the APIs. Now the question is that how can user easily control this kind of interaction between the test generator and the effectful system, but still do the smart exploration with guidance? Let's take a concrete example. Assume the system we consider is a system that can parsing, type checking, and do the interpretation over some language terms. Look like this. the test generator can using this parsing of API to construct AST consecutively, and also can do type check and evaluation. The point here is that in the if-helpful system, the test input is not a data type or not an AST, but some traces of events. So the language term we consider in this example is simply type lambda calculus, STLC, with the Bruegel index. So people probably more familiar with the STLC term with the named variable like this. You have X and Y, which actually refer to previous STLC abstraction bindings. However, that is not closed under this alpha renaming. You have lots of variants. So the Bruegel index can unify them using this, where we don't use a variable name, but we use the index. The 0 index refers out the closest abstraction, and 1 index refers as the outer abstraction. So the Bruegel index does the unification, but also makes it tricky to implement a correct interpreter within it. So concretely, we want to test the interpreter API in the system, and the property is the wild-type STLC term cannot get stuck. So the potential bug is the interpreter probably use incorrect substitution. Here's the STLC term, and you can imagine the test generator send the input event, say eval, and the evaluation gets stuck. That is ill form because index 1 tries to refer to the outer abstraction, but there's not an outer abstraction. The point here is that the only STLC term with a very specific shape can trigger this bug. You need to have application, otherwise this substitution will not happen. And you should have the non-zero Bruegel index. And also to make sure the non-zero Bruegel index, you need to have the nested function. So how can we construct such kind of input? For if-helpful systems, still we don't directly provide the AST. In order to construct this nested function, the test generator do interaction with the system. Assume the system originally stored AST with unknown node, and the test generator say, I want an abstraction with net-to-net type. And the system then return the depth 1, that is the depth of the nested function, and transfer to another state. You can see this ASCR change. And you can say the test generator want to another abstraction, and then want to abstract application. You do that consecutively. That's the way you construct this AST in an interactive style. So the question is that, how can we do this directly property-based testing? Or more concretely, how can user easily control this kind of interaction? So the first challenge is that people need to specify this basic correctness and searching bias for actually the trace of events, not the data type. Assume this is a trace of events, and people need to specify like val typeness, and that need to exist in nested function application. The second challenge is how can we check, how can we ensure a test generator indeed do this text exploration following the guidance provided by the human. This kind of a correct test generator are hard to write and also deliver more user burden. So we try to do that better. We actually try to synthesize the correct test generator that is correct by construction. Let's move on to the first challenge about the specification. We introduce a notion, what we call the local specification. The global specification is exactly the property you want to test against, and it encodes some basic correctness, like val typeness. The local specification is a spec for each API or each event. For the API eval, it means that in order to trigger the dangerous substitution, there at least need to have an application. And we also have the specification for ABS or the var, the encoding some Bruegel index semantics or val typeness. So the whole workflow is that the user provides a global property and local specification. Our synthesizer, we call it Crusoe, synthesizes this generator for user. The point here is that the user don't need to provide potentially complex search bias, where our synthesizer can infer it from this local specification global property. because our local specification encodes the event dependency. So how can we specify the event dependency? We introduce a specification language called U-heads. The heads is the previous works, is a refinement type system equipped with a pre and post condition in a Horner style. It's have a parameter type and return type, but also have P and Q. Like Horner logic, but it's quantified over traces. We want to highlight that the P and Q are not just regular expression, but it's a symbolic one, which is rich enough to express more complex constraint, like the arithmetic relation in the divergent index. And this specification, or approximate, describes the safe behavior of an API. For our setting, we take an under approximation variant of the heads, where it describes a subset where a test generator must be covered. And there's also have must-del semantics. It say, to generate the trace satisfies the post condition Q, there must exist trace in the precondition P. I can give you an example of the U-heads. For example, the var, you can see have a pre and post condition like this. It's actually have an event dependency. The var actually refer previous abstraction in the ith outer level. So this one is correct, but this one is not, because this index 1 doesn't have any outer abstraction here. So also have a must-del semantics. It say, to get a non-zero index, there must exist a previous nested function abstraction. Let's move on to the second challenge about the soundness. We first introduced a DSL for our input generators. In order to make sure this test exploration provide a correct divergent index, our test generator need to actually observe the output events from the system, like the depths. We store that as a variable d. And we have assertion. We assert this depth as a valid depth. Otherwise, we even detect an error in this parser API. And we have random generator and assume, which can make sure this new index are valid divergent index. The point here is that our language is a solver-aided one. So we can use this assembly store like this array to deal with the assert and assume. After that, we can safely call this var to generate the input event and send that to the system. More interestingly, our DSL have recursion and non-determinist choice. This is sufficient enough for us generator to explore a family of interesting traces following the guidance. So our type soundness says the synthesis test generator should be consistent with both global property and local U-heads. Assume that is a trace generated by our synthesizer generator, and the whole trace need to represent some well-typed STLC term. And if you focus on one specific event, which divides the trace as a prefix and postfix, this is consistent with the P and Q within the U-head of a var. Let's move on to the challenge about the synthesis. We derive a type-guided synthesis algorithm where is a correct by construction. So how can we guarantee the synthesis generator are consistent with the global property? We take the global property and actually convert it into a candidate generator. That's exactly a program in our DSL, but with some holes. You can see a well-typed program need to be either be basic type or arrow type. So we can see there are two branches. And the next challenge is that how can we make sure that it's consistent with the local specification? Let's take a look at the first branch, for example. We actually try to fill the events into the program holes. So our algorithm have a refinement loop to fill this program hole consecutively with events. For example, like this, you can find this is not quite right because we said that the var need to refer some abstraction, which is missing. What we can do, we take the U-heads of the var, which have to encode the event dependency in the precondition automaton. And you can merge this U-heads and the candidate generator to get a new candidate generator where this ABS actually fill into this program hole. You do that consecutively and until all the events are consistent with this local U-heads. So that is how we make sure that it's a correct by construction. Let's move on to the evaluation. The first research question we care about is expressiveness. Our tool Cursor actually can target it to multiple backends. One backend we consider is OCaml backend, which has the QChat as a property-based testing framework. In this backend, we focus on the sequential program, but also in a very diverse domain, like effectful data structure, in serialized data like SDLC, and even database. You can see all these are sequential program, but the datasets even have some concurrency constraint. Another backend we consider is P language, is automated reasoning language for distributed model. So this is a quite different setting. It's not sequential program, but actually we have a set of nodes in the distributed system, and each node are implemented as a state machine. This state machine can send message and receive messages. So for this benchmark, we select the well-known distributed protocols. And all of our benchmarks are selected by the prior works. You can see they are quite diverse. We also care about the user input. The user need to provide additional U-heads. For each U-head, we actually count the complexity by how many data dependency constraints encoded in this U-heads. In average, each U-head user need to provide 3 constraints. This means that Cursor doesn't require a lot of user inputs. And the synthesis overhead is also low. The average synthesis time is less than 3 seconds, and the maximum time is less than 3 minutes. And we also achieve a good performance. We count the bug detection rate. For 2 groups of benchmarks, our synthesized generator by Cursor can detect 100% bugs, although our baselines, the random generator and the human random generator, are relatively low. We want to point out that the human random generator are well designed. They actually encode all this guidance manually. And within all the cases human generator can find a bug, our synthesized generator can do that much more faster. Okay, let's move on to the summarization. Our tool Cursor allows users to encode the test exploration guidance into our specification language U-heads that can specify event dependency with the master semantics. And we introduced a DSL, which is statically typed solver 80-1 for the effectful generator that's supporting very diverse domain. And we'll have a type-guided synthesis algorithm, which can leverage the basic correctness and the searching bias from the global property and local U-heads. Thank you.
All right, we have some time for questions.
Hi, Harry Goldstein, University at Buffalo. Thanks for your talk, very nice. I'm wondering, you talked a bit about effectful programs, but then you were talking about STLC, which I don't usually think of as particularly effectful. So can you talk me through like where the effectfulness is and why this is like what makes this problem very distinct from the problem of just generating STLC terms normally?
Yeah, so if I understand your question correctly, is that you think this SLC is not be traditionally treated as an effective one, right? The thing here is that in our setting, as what we show in this slides, we don't directly provide this EST, but EST actually some stored in the state of the system. And you can like do that like the objective-oriented language that you can construct it, mutate it within the different interaction between the test generator. I agree, you probably have a different kind of a style to encode the whole progress. For example, you can directly generate this EST. But our targeting is a serialized data. Like you indeed have a parser, right? You can imagine the parser take a sequence of a token, and the order of the token are quite important. So it's not just EST. Does that answer your question?
Hi, thank you for the talk. I'm a PhD student from Z Boulder. I have a question on, so if the user need to write the UHAT for the verification process, then if it fails due to some like with our own specification, do you give any some like counterexamples or feedback to users?
Yes, so if I understand correctly, you mean that when the user provides the wrong UHATs, what happens? So there's several kind of error we can define. One error is that the UHAT is totally make there is no existing synthesizer exists. It's probably self-conflict. In that case, our synthesizer will detect it, find there's UHAT are conflict with each other, and we will provide a concrete instance to it. Another kind of wrong UHAT is that, for example, our UHAT assumes this parser have a debugging index within the system, but it's totally don't have such a guarantee. So the UHAT didn't really align to the system behavior, and that will cause a runtime error. Just like our DSL, we have assertion. I remember I mentioned that if the system returns a wrong depth, we can also detect it. Does that answer your question?
Are there any other questions while the next speaker sets up? All right, let's thank the speaker again.
There we go. Okay.
All right, our next speaker is Kavya Chopra from ETH Zurich. I'll give you 5 minutes and 1 minute. You have 5 minutes left and 1 minute left.
Okay, sure. Let me know when to start. Yeah. Hi everyone, my name is Kavya. Today I'll be presenting my work, Semantic Reification, a new paradigm for random program generation. As we all know, compilers are huge, complicated pieces of software, and sometimes things can go a little wrong. Your compiler may cause your program to hang, miscompile, or even crash. And these optimizations, while they improve performance, they occasionally introduce bugs as well. Now, differential testing gives us a simple oracle to find and snuff out these bugs in programs. You take a program, you have a reference compiler, and you test out the same program at different optimization levels with that compiler. If the outputs differ, something's amiss and you have a bug on your hands. Now, differential testing itself is easy, but the hard part is actually generating these random programs. The thing with generating these random programs is that if your random program accidentally happens to have UB, the compiler can do anything, including making the proverbial demons fly out of your nose. However, what we want to do over here is generate random programs that are A, syntactically valid, B, UB-free, C, deterministic, and still nasty enough to test out and stress test the gnarly regions of your optimizing compilers. Now, previous work in this area falls under a paradigm that we like to call syntactic reification. C-Smith and Yapgen are fantastic tools that have successfully found hundreds of bugs across GCC and LLVM. They work under the same premise, which is you have a context-free grammar, and then you generate statements from that grammar. Now you have a program which you feed back into a layer that filters out for UB in these programs. A couple of iterations of this loop back and forth, and you finally have a valid C program. However, despite these generators being extremely powerful, this UB prevention layer often causes some restrictions. For example, C-Smith has conservative analyses and runtime guards to help it avoid undefined behavior. Yapgen constrains loop iterations so that they all behave predictably and in a similar manner. These existing generations miss unbounded loops and irreducible regions. Unfortunately, these are precisely the kind of constructs that are notoriously hard to optimize and reason about and make compiler writers stay up at night. It is these kind of constructs that we also wish to model in our programs.
Arbitrary control flow is our solution to having both these kind of constructs in our programs. Now, we don't just want arbitrary control flow because it sounds good, but because it's integral to testing out optimizations such as loop invariant code motion, code hoisting, code syncing, value numbering, IV ops, and so much more. We have harder, these are all important because these optimizations help track how values flow through CFGs. So when you make your CFGs arbitrarily more complex, it gets harder for the compiler to reason about these optimizations as well. And this is exactly the kind of thing that we want to test out. But again, it's very, very hard to generate these programs with arbitrary control flow. So the million-dollar question becomes, how can we generate these programs with arbitrary control flow while still guaranteeing correctness, definedness, and termination? Our solution to that is a paradigm called semantic reification. Some semantics gets thrown around a lot. So what exactly do we mean when we talk about semantics? We talk about largely two kinds of semantics over here. A, compile time semantics, which is what a program can do and what your compiler has access to. B, runtime semantics, which is what your program actually does at runtime. To model both of these semantics, we have proxies. Firstly, we have the CFG skeleton G, which is the CFG of a program stripped bare of its statements. So effectively a bunch of nodes and a bunch of edges. To model the compile time semantics. To model runtime semantics, we have an execution path pi of this program, which is just the path pi sampled through this graph. Then we put both these inputs into our magic semantic reification synthesizer, and out comes three things. Firstly, a program P. Secondly, a program input I. And lastly, a program output O, such that the CFGs of this program P has the same skeleton as that of G, our input CFG skeleton. Executing P on this program input I makes it follow the execution path pi and ensures that the execution is UB-free and terminating. Lastly, program output O. Executing P on this program input I ensures that, that the output we get is the program output O that we give you. So the key capabilities of semantic reification are threefold. Firstly, we give you arbitrarily controlled flow because now you have full control over the CFG skeletons you wish to feed in, over the execution paths you wish to feed in. Secondly, guaranteed semantics by definition. And thirdly, an established oracle. Whenever you put this input I into your program, you know exactly what's about to come out. Now, we proceed to do this using symbolic execution. And this begs the question, hey, how can you generate whole programs using symbolic execution? The path's going to explode, your SMT formulae are going to be really large, and the program is just, and the generation is just not going to scale well. To solve that, we decompose our program writing into two parts. Firstly, we generate functions that are small enough that they can be given, that outputs are tractable enough to be obtained from these solvers and symbolic executors. Then we compose these smaller functions into larger programs using something that we call peephole rewrites and call graphs, something that I'll talk about during the later half of my presentation. So the idea is to use semantic reasoning where it matters and to optimize for scalability where it doesn't. Our implementation of semantic reification is a tool called Refi. Refi is a 5-step tool which first generates CFGs, samples a path through them, creates a symbolic function, concretizes it, and then uses many of these symbolic functions and composes them into whole programs. I'll walk you through an example of precisely how we proceed to do this. Firstly, we generate or borrow a CFG skeleton. Graphs are available on the internet aplenty. Real-world code has a lot of CFG skeletons. You can either take it from them, or you can use our in-house graph algorithm. All we had while generating graphs for ourselves was was modeling basic blocks as nodes and edges as possible control flow transfers. Our soft constraints was just keeping the graph usable so that it doesn't turn into spaghetti code. And our hard constraint was that the entry and exit should have a path that connects both of them so that we have at least one valid value of pi to feed into our generator. This helps us guarantee arbitrary control flow. Second, we sample a runtime path through the CFG. For this particular example, we're sampling the path entry, B1, B3, B1, B2, and then the exit. The path says what the program actually does on this input. This enables arbitrary execution, including loops, repeated blocks, and any path as convoluted as you can think of. Thirdly, we create a symbolic function. Cool, we have a CFG skeleton. It's time to fill it in. The initial IR we used to fill in these functions was SimIR, which was a minimalist IR that had addition and multiplication for 32-bit C integers. We've expanded the scope now, but let's keep it to this for now. Now, you'll see on the statements that there's multiple symbols over here. You'll see int a equals S1, C equals S2. A, B, C are variables. B1, B2, B3 are basic blocks. We understand that part. But then, what are S1, S2, and S3? Well, S1, S2, and S3 are knobs that you give to your solver. Currently, the symbolic function that we had in this slide was a program template and not a program itself. When we have S1, S2, and S3, we can use these to write our constraints that the program should follow and then feed them to an SMT solver. These are knobs the SMT solver will control and tell us what the value of these should be in order for our program to give us the guarantees that we promised you. But how do we actually go about generating these constraints? Well, you have a symbolic function, you have a path. How do you generate your constraints? Quite easy, actually. You just unroll your symbolic function along the chosen path. For example, let's take the subpath B1, B3, B1, and B2. Initially, all variables start off with their initial values, A0, B0, C0. Look at block B1. When you're assigning to C, its value gets bumped from C0 to C1. And similarly, look at B3. After B1, we're going to B3. We now have C1, A0, and B0. B3 assigns to A. So now A gets bumped from A0 to A1. Similarly, when we go back to B1, we now have C1, A1, and B0. And when we're bumping C again, now we bump C from C1 to C2, and the value for A we use is no longer A0, but A1, as was initialized in the previous block. So in the CFG, the blocks are the exact same, but there are different moments of time. And this is exactly what we wish to capture with these subscripts. Then we generate the constraints for our unrolled path. We have largely three categories of constraints that we would like to focus on. Firstly, definedness. These are the constraints that actually help you evade UB, including but not limited to integer overflow, division by 0, and the like. For us here, A0 S3 plus B0 S4 plus S5 and all sub-expressions of it should fall between int min, and int max for the definedness constraints to hold. Secondly, computation. We also wish to respect the operational semantics of the C language. So if C is indeed being assigned as A times S3 plus B times S4 plus S5, we wish to respect that and encode it in mathematical language as well. Lastly, and this is the constraint that distinguishes us, termination. Termination helps us mold exactly where we want the program path to go. We want the program to go from B1 to B3. Sure, C1 times S6 plus S7 should be less than equal to 0. This is what can help us ensure that the edges we want exactly are taken, and this is what helps us ensure that the program exactly follows pi. Now, voila. Feed all these constraints to the solver, and you have an output. Now you have an output for all the symbolic values that you initially wanted. You put them back into the program, and now, hey, you have an actual symbolic function, a program input and a program output, with the guarantees that these are UB-free because of our definedness constraints, terminating because of our termination constraint, and follows pi again because of the termination constraints. Now, how do we use these smaller symbolic functions to generate whole programs? You have a random call graph, and that can be used to link functions. For example, main here calls func. So how do we link both of them together? Well, you know the output of func on a given input, so you just do some offset addition. So for example, func on this input gives this output, which in turn added with int max minus 1 gives 32. This is exactly what we substitute in here. But hey, why are we doing these peephole rewrites in the first place? Aren't smaller functions sufficient to test out optimizations? Well, there's a lot of inter-procedural optimizations out there that we also want to hit, and this is precisely why we do this. And here's the kicker. The example that we've been walking through all this while was an actual real GCC wrong code bug that we found. This was because of some errors in the scalar evolution and IV opt passes. In terms of bug discovery, we've had 59 total bugs with 57 confirmed and 27 fixed. Recently, we found more than 15 additional bugs in GCC and LLVM. What kind of bugs did we find? We found long latent bugs, we found high priority bugs, but more importantly, we found bugs that exercised complex control flow and exercised diverse passes in the compilers. Now, the coverage that we have is complementary to existing tools. You'll see that newly covered functions mainly involve inter-procedural optimizations, shout out to peephole rewrites, and CFG transformations, which is something that we claim as our own unique contribution. The reason existing tools missed these bugs was because they were a little conservative with the static analysis, runtime wrappers, no irreducible loops, and identical loop iterations. What we provide uniquely is arbitrary control flow with unbounded loops and irreducible regions. This is what makes me believe that semantic reification is a very promising complement to syntactic reification and has great probability and propensity of catching bugs, which syntactic reification has not caught yet. To really hammer the point in, here's a small bug example that shows irreducible control flow. You'll see that block K over here is an irreducible region. And this is something that syntactic generation could never have generated for us. So this is our unique contribution which helped us find a bug in this particular domain. In terms of implementation and some stats on scalability, Reifi is 7,000 lines of C++ and uses C3. Currently, we only supported C with 32-bit integers and arrays, but we're expanding. And we also ported to Java bytecode and were able to find 3 bugs in OpenJ9. The SimIR that we have developed is language agnostic. In terms of performance, the majority of the time, of course, is taken by generating the symbolic functions because the SMT solving takes that long. But we have, of course, minimized the impact of that using our whole program generation, which we do using peephole rewrites and not symbolic execution. Beyond the paper, we have RefractIR, which is a work-in-progress extension of SimIR. We now have first-class symbols, arbitrary precision integers, floating points, vectors, first-class intrinsics, etc. Reifi's pre-implementation based on RefractIR found 10 bugs in GCC and LLVM within 1 week of running. In terms of future directions, we see this work going twofold. Firstly, implementation improvements, which is a richer feature set for RefractIR and just faster solving for SMT. In terms of scope, though, we don't think semantic reification should be limited just to compiler testing. We feel that it can be used to validate static analyzers, debuggers, program verifiers, languages, runtimes, and the like. The key takeaway is that semantic reification makes program generation less about hoping for interesting behavior and more about constructing it with guarantees. Thank you so much. I'd like to welcome any questions now.
All right, questions?
Hi, thank you. Great talk. James Lee Jones from Imperial College London. So I can imagine that generating programs in this way can be fairly slow if you're relying on SMT solving. And I wonder if you considered combining this with techniques, which actually I think from your group, like equivalence modulo input testing, so that you only do the slow sort of generation once, and then you get the extra benefit of generating more programs and not having to go back through the SMT solver. And I guess also just one clarification. So I think you mentioned somewhere along the way that you avoid generating undefined behavior on the path that you take. But I guess it's important actually that you have no undefined behavior anywhere in the program. And I just wanted to clarify that that's actually what happens, that your programs are guaranteed UB-free everywhere, not just on the execution path.
So the guarantee that we do give over here is the program is indeed UB-free only on the execution path. You can take a different input, and we don't guarantee that it's going to be UB-free. It can hit whatever we want. As far as EMI is concerned, I am not super aware of that. Maybe Song can give more insights on it.
Basically, what we have ensured is that given the specific input, the execution of that program is UB-free. But if you give it some random input, we cannot guarantee that because UB is a dynamic behavior. And for those like basic blocks that has not been enriched, either at the runtime or at compile time, we want the compiler to infer them, to infer some information like the reachability, like define use chains from them so that it can perform some like stressful optimizations, aggressive optimizations, or even infer some information that it thinks useful, but actually is buggy, and so that we can find the bug. Thank you.
All right, I think we have time for at least one more question.
Hi, thank you for the talk. I'm a PhD student from Seaboulder. I'm not sure I understand correctly, but in your slide, you said that you're generating a function with a single pass symbolic execution. Is there any like restrictions due to the single pass symbolic execution? For example, if you use the original symbolic execution to generate the function, can you generate more complex functions than now?
I'm not sure I understand the question, sorry.
I mean, like, is there any some like the the behavior restrictions on functions. So, but because of the single pass symbolic execution. So yeah, that's my question.
Yeah, sorry, you can go first. Yeah, we did try multiple path execution, but again, it's just like more constraints on the SMT solver, and it was a little more intractable for it to solve. That's why we decided to stick with single path for now.
It is also possible to like use full like symbolic execution to generate the program. But one thing is you have to model the constraints for different path. And the second thing is you have to consider the performance of the solver. For a full symbolic execution, I don't think the solver can handle it for a large program. Even for a small function, I don't think it can handle it very well, especially when you're adding more like features, like vectors, like pointers, like arrays, indexing that makes the solver very, very like stressful. But I think it's also possible, I'll see. Yeah. Thank you.
I think we can take one more question while the next speaker sets up. Actually, I had one question. It seems believable that you can take an arbitrary CFG and reify it using GoTo. But if the particular CFG is able to be synthesized using while loops or for loops or something, are you able to recognize that? Or do you always just use GoTo?
We do have some support for like having more reducible loops in our program as well.
Okay. All right, let's thank the speaker again.